So, assuming I'm smart, I've made these high aspect ratio structures. The next big problem is how do I fill them, right? So, filling them is another problem. So, we want to fill some of these STIH with dielectrics. Sometimes we etch dielectrics and we want to fill them with metal. And the important two parameters which describe how good at I am at filling them is what I call as the bottom step coverage and the side step coverage. So the bottom step coverage means how deep I deposit at the bottom divided by how thick I deposit at the top. The side step coverage equivalently means how thick I deposit on the side divided by how thick I deposit on the top. And ideal conformal process would be essentially which deposits the same amount on the bottom as the top, and it deposits the same amount on the side as the top. So in an ideal world, you would want your bottom step coverage to be 1 and your side step coverage to be 1 as well. Especially when you have dielectrics and you're depositing liner materials on them. So if you are doing a back end of the line process, you have essentially a mold of silicon oxide and you want to deposit maybe a tantalum nitride barrier. So you would want it to be very thin, a nanometer thin, and you would want it to be very conformal, right? So that's a problem. How do I, so this is showing something which has an aspect ratio of maybe it looks like 1, but in reality I have these aspect ratios of 60, and I want to deposit very thin liner materials, or I want to fill them with a dielectric without causing a void. So that's the other point I want to talk about, that is to how to fill these high aspect ratio structures. Let's look at all the tools we have at our disposal, right? So one thing I could do is PVD, but PVD again is a very it's a line of sight process. So essentially, you have these one evaporator, and you have these ions coming from that target, and it's something which has very poor conformality. So if I had a PVD process, essentially very little will come to the bottom, and a large thickness would go on the top. So it would close out very soon, and you'll get this void in between. So PVD is, of course, not the process to fill this high aspect ratio structures. Right, so how about other deposition techniques? So how about CVD? So CVD, again, it can operate in many regimes. It could be operating at a regime where you have so one of the important things in CVD is this thing called sticking coefficient. So if an ion comes, what is the probability that it sticks to that surface? So if I operate at something which has a high sticking coefficient, then basically if something comes here, it would just stick over here. But if I want to fill a high aspect ratio structure, what I need is I need to be operating in this regime, which has a sticking coefficient of, let's say, 0.05. So it goes through 20 reflections before it sticks on something. So to fill this high aspect ratio structure, one thing that people do is to operate use CVD process in these regimes which are at very low sticking coefficients. And this is shown over here. So this is showing your step coverage as a function of sticking coefficient. So if I have a sticking coefficient of 1, essentially you will close out very fast and you will cause a void. If you have a sticking coefficient somewhere around 0.4, you will cause a profile like that. If you have very low sticking coefficient, you can fill it up without causing a void. So this is something which is, again, most commonly used to fill up these high aspect ratio structures. Sometimes many a times you want to deposit these liner layers. So we want to deposit, let's say you're doing electroplating of copper, so you want to deposit this this barrier layer, which is tantalum nitride or tantalum, and you want it to be very conformal in this high aspect ratio structure. So the thing which comes to our rescue, or the only tool available for doing this, technique available for doing this, is atomic layer deposition. Atomic layer deposition, of course, it has an ideal step coverage of 1. It's the same thickness on the bottom, on the side, and on the top. The disadvantages of atomic layer deposition, it's a very slow technique. You have to pulse one precursor, you have to pulse the next precursor, and it takes hours to deposit a few nanometer thick film. It's high resistivity. Most of these films, even if you deposit metal films like tantalum nitride or tinitride using ALD, these films are amorphous, and by default, if you're using ALD, you get amorphous films and they are high resistivity. The other thing, especially if you're depositing metals using ALD, is most of the metals are solid, right? So if you want to do a ALD of a metal, you have to make it you have to make a precursor which makes this metal evaporate. So what you do is you attach these carbon groups on your metals that are your ligands, and essentially you evaporate that metal, bring it to the surface of this structure, and then you want those organic groups to leave. And at best, even if they all leave the surface, you are left with carbon contamination of the order of 1e16, 1e17 atoms on your surface, and that essentially again increases your resistivity of your film. So even though you're depositing metals, they end up with resistivities that looks like they are dielectrics. So that's a disadvantage of ALD. So this is a really cool technique, and this is actually something which has really emerged in the last few years, is that most things become worse when you go to smaller dimension or when you go to high aspect ratio. But there's one force which scales inversely with the small structure, and that is your capillary action. So you might have done this experiment in your high school. So if you dip these different tubes into a mercury bath, the structure which has the smallest width gets the highest, the highest bar of mercury because of this pressure from the atmosphere. And these capillary forces essentially scale up as inverse of your radius of your tube. So if you have the smallest tube, it would have the highest height of this mercury bar. So it's the same thing we can leverage in filling up some of this structure. So there's this process called as Reflow, and it's becoming increasingly popular to fill up these high aspect ratio structures. And I've posted a video on the class site which describes this. So what you do is essentially, if you have this high aspect ratio structure and you want to fill it up with copper, you just do a PVD of copper and it deposits on the top. And then what you do is get your copper in a state such that it's not liquid, it's not solid, but it's somewhere in between, so it can flow. And once it can flow, it essentially flows up into this trench, and that capillary action will force most of your copper, or it will essentially exert a higher force on the trench, which is the narrowest. And that's a very effective way of filling up these trenches with high aspect ratio. So this is currently, people are using it for filling up copper in back end of the line structures. This is not just limited to copper. People also, for your dielectrics, say you have a STI trench and you want to fill it up with dielectric, you deposit these dielectrics which are in this state between being a liquid and between being a solid, and they essentially flow into it, and this capillary force pulls that layer into your high aspect ratio structure. Again, a very cool technique. This is something which is which just scales beautifully as you go to even higher aspect ratios. Yes. I don't want to, but so most of these metals, right, they're not in gas state. They're essentially solids. So for ALD, you need a metal precursor, right? You need some, like if you have Al2O3, the way you deposit is aluminum is you have TMA or trimethyl aluminum. So you attach three methyl groups to aluminum, and that TMA is essentially a volatile species, right? and then it comes on the surface, and then those water group, those methyl groups leave, and you're left with aluminum on your surface, right? So what I'm saying is that those methyl groups or those carbon groups, they 99% of them might leave, but some of them will stay, and that's enough to give you a lot of carbon contamination. Yeah. So you need to make things volatile, right? So the easiest way to make things volatile is to attach these organic groups, and then it becomes volatile. So the other theme that I want to cover, and I want to cover a lot of things using that, is parasitics. And by parasitics, what I mean is these resistances and capacitances that we don't need, but we get them anyway when we scale our device. So this is showing the Intel FinFET transistor. So if you look at these numbers that essentially every company will plot out when they publicize their technology. So if you do some back of the envelope calculation of these numbers, so it says that their PMOS has a saturation current of 1.1 milliamp at 0.8 volts. So if you do 0.8 by 1.1 milliamp, it gives you a resistance of 72 ohms per micron. Similarly, for NMOS, it's around 64 ohms per micron. And out of this resistance, it has different components. So it has the channel resistance, and it has these other components which are parasitic. So in the current technology, out of that 72 or 60, around 20 or 30 comes from this parasitic resistance. That's your contact resistance and your diffusion resistance. So even if you get rid of the channel, the maximum current you can get is only thrice, because these parasitics, which will essentially eat up all your current gain and all the beautiful things that you do to your channel, the strain you put or the higher mobility you put, it just gets washed out because it's connected in series with these other parasitic elements. And the interesting thing which has been happening in transistors, especially for logic transistors, is that there's no room left to put any contact. So Moore's law essentially says that you scale your gate pitch by half every technology node, but your gate length does not really scale by half every technological node. It scales more like 0.9x. In fact, since last few technology nodes, it hasn't been scaling at all. So if you look at that pitch, you'd have to leave some space for spacers around your gate. So the rest is the space. This green thing is the space which is left for your contacts, right? So in a 90 nanometer technology, you had 120 nanometer of space available to land these contacts. On a 30 nanometer technology, you had 32 nanometer of space available to land these contacts. If you go by that same projection on 20 nanometer technology, you have no space to land your contacts. So you can make a transistor, but you can't connect to it. So that drives this other thing that I want to talk about, that is self-aligned contact. And by self-aligned means that your source and drain are now, they can now have a misalignment with your gate, but they will still make contact to your transistor. Another thing which is driving them is this slide that I'm borrowing from Sam, is that you have misalignment between these different layers. So these contacts would now be on 3 different masks, and each of them would be misaligned with respect to my gate or with respect to my active regions below. So inherently, I have to build up a scheme which is immune to this misalignment. And self-aligned contact is a way of doing that. So this is what I mean by a self-aligned contact. So we use a high-K metal gate. So your gate nowadays is essentially metal. So if a contact comes and lands on top of it, it will essentially short your source and your gate, right? So to prevent that from happening and for implementing the self-aligned contact scheme, you etch that metal back, and you fill it up with a nitride. So you have this metal buried under your nitride. And now essentially you're ready for this scheme called self-aligned contacts. So now what can happen is your contact can come and it would be misaligned. It would be either misaligned this way or misaligned that way, but part of it will still connect to your source and drain. And remember, these gate lithography and the contact lithography are the two smallest lithography steps with the most aggressive feature sizes. So inherently, there's a lot of misalignment built in. So this was introduced by Intel at 22, and you add this 3 extra process steps. You etch your metal, you fill it up with nitride. But now essentially, your contact can land on top of your gate, and you will still get some current out of your transistor. So this is a chart showing that this is actually showing a picture where the contact, the person who was doing the contact lithography, maybe he was not having a good day. So you can see that these contacts are not having the best alignment, and they're misaligned by a large distance. But the part of the contact is still landing to your source and drain, and you can still get some current out of it. So in a non-self-aligned scheme, essentially if you had that much of misalignment, you will just short your source drain to your gate, and your yield of your chip will just go down in this Gaussian pyramid. But if you have a self-aligned scheme, you could tolerate even 20 nanometer of misalignment, and you'll still get some current out of your transistor. So that's one of the main motivation for going to self-aligned schemes. And turns out, Intel announced it at 22 nanometer, but again, I want to bring up this point that DRAM, NAND, logic, they keep up borrowing ideas from each other. So DRAM people have been using it for a while, so they had these more systematic layout, sorry, not the DRAM, the NAR flash people have been using it since 45 nanometer technology, and they have these well-defined layout where you have these cells, and each of these bit line contacts has to come and land between two adjacent cells. And clearly enough, you can see this experimental picture where your tungsten contact is self-aligned between these two transistors. And the DRAM people have been using it even before that, few years before that. So we did this problem in a homework where we identified that in a DRAM you need to have a bit line contact which is shared across two capacitors. And so this bit line contact will land in between your transistor and your capacitor. And they have been using this self-aligned scheme where essentially, since it's a very regular layout, you'll have these regular misalignments, and it can land on top of your gate without shorting your gate, because your gate is covered with this protecting layer on the top. So the gate contact is made, actually very good question. So the gate contact is made behind. So it's not made on the same plane, but it's made like behind this plane. So it would be connected somewhere. And especially since this metal itself is a local interconnect, right? So you don't, if you have like a SRAM cell, these two metals gate would be just connected by this metal gate, right? But when you are landing another layer on top, it would be connected, but it would be either in front of this or on the back of it. It wouldn't be at the same, they wouldn't be at exactly in between the two. So this is something we don't desire, and it's something which comes with its own consequences which are not necessarily good. So a bad consequence of going to this self-aligned scheme is that you get a much higher parasitic. So you are essentially bringing these contacts very close to your gate, and that essentially increases your gate to contact capacitance. And this is showing a result where your gate to contact capacitance becomes even bigger than your gate to channel capacitance. And these are bad for CMOS, but they are even worse if you're making analog circuits. These are essentially what contribute to your Miller capacitances, and you, um, it's just bad from a parasitics point of view. This is another thing showing that you had these different layout, and this is the SRAM layout. So you had a certain amount of capacitance between these different elements when you were at lithography aligned contacts. But when you go to a self-aligned or SAG scheme, all these capacitances shoot up. So it's a very bad scheme from parasitics point of view, but there's no other option because there's no free lunch.